Welcome to this lecture series in real analysis. In this lecture, we'll be proving the very important mean value theorems, and primarily what we need to know is the following fact. Suppose we have a continuous function defined on a closed interval a comma b, and assume that, what have I written? Assume that f is differentiable in the interior of this interval, meaning in the open interval a comma b. Then if f has a local extrema at an interior point, meaning a point here, then the derivative of f, which exists by hypothesis, the derivative of f at the point x0 is 0. So we proved this, and pictorially it's very, very clear. You maybe want to draw a function like that. So if it has a local extrema here, clearly the derivative visually seems to be 0, and we proved it. Okay, so let's proceed. So here's the first theorem, known as Rolle's theorem. I think historically things have been very interesting. Rolle was a critic of Newton's work. He did not agree with the calculus that Newton developed. I think something like that happened. It's interesting. You should Google and maybe see the Wikipedia article. Alright, so what does it say? It says that suppose we have a continuous function defined on this closed interval a comma b, and again assume it is differentiable in the interior of it. Then if the values of the function are the same at the endpoints a and b, then there is a point c in the interior of the interval, meaning in the open interval a comma b. We have called such a point c with the property that the derivative of f at c is 0. So let me explain via pictures. So the picture is something like this. We have a continuous function which takes the same value at a and b, and we want to say that somewhere in the interior, somewhere in the middle, the derivative vanishes. Intuitively, it's quite clear. All we are saying is that somewhere if you keep bringing this line up and up and up, at some point it will start touching the curve, something like that. So intuitively, it's not much of a challenge. What is the seed of the idea? What is the main idea which allows us to prove this? The main idea is that we can show, and we will show, that somewhere in the interior, the function will obtain or attain a local extrema. Once we prove that, we can just use the theorem we just recalled in the beginning. So that's the point. Show that it attains a local extrema somewhere in the interior. This hypothesis then helps us prove what we want to prove. So how do we do that? There could be many ways to execute that, but perhaps the simplest is first to translate the function so that fa and fb are both 0. It's just a suitability thing. So we are translating so that the function takes the value 0 at a and b. What was the hypothesis? The hypothesis was that if fa equals fb, so it takes the same value at a and b, but it is convenient to have that value equal to 0. So the first step is, without loss of generality, assume that fa equals fb equals 0. Okay. Now, if f were the constant function 0, if f were the constant function 0, and let me write it succinctly, if f is the constant function 0, then clearly we are done. Why are we done? Because then everywhere inside the derivative would be 0. The constant function has derivative identically 0. So if this were the case, then we were done. So we may assume f is not constant. So if f is not constant, it has to deviate from 0 somewhere. It already takes the value 0 at a and b, and if it is not a constant function, it has to take a non-zero value somewhere. Again, doesn't matter whether that value is positive or negative, so we may just without loss of generality assume that the function takes positive value somewhere. Without loss of generality, assume f takes positive value somewhere at some point in this part, open interval a comma b. Right? At a and b, it is taking the value 0. So, since we are assuming the function is not constant, somewhere in the middle, it has to take a non-zero value, but we may, without loss of generality, assume that it takes positive value. Okay, and now we will just say, let m be the supremum of f, or the values of f. I mean, this is just another way of saying take the supremum of the image of f. Image of f is a compact set. This is a compact set, so the image of f is a compact set. In fact, it is a closed interval because f is continuous. So, its supremum exists. This is a real number. So, let C be a point. C be a point in a comma b. Yeah, so before I write that, so since f is assumed to take positive value somewhere and we have taken m as the supremum, we know that m is greater than 0. So just observe that m is greater than 0. And now, let C be a point. It has to be in the interior such that, let me complete the statement and then I'll justify. C be such that f of C equals m. So, the supremum of the image of f lies in the image of f. Image of f is compact. So, this value is there in the image of f. Right? So, there is a point in the domain of f at which the function attains that value m. Because m is in the image of f, there is some point in the domain, some point c in the domain such that f of c equals m. Now this point c has to be here. It cannot be a or b because at a the function is 0 and at b the function is 0. M is positive. So the point c has to be here. That's all. Okay, and now we can just use what we recalled. Yeah, so now note that f has a local rather than local. In fact, it's a global extrema, maxima in fact. Global extremum at C, and hence the derivative of f at C is 0. And that finishes the proof. It was a very simple proof, but I gave all the details. Okay, it's an intuitive theorem, a useful theorem, and a very simple proof. Alright, so let's move forward. So this is a small generalization of the previous result. Suppose we have a continuous function, again defined on a closed interval, and with the same hypothesis. Assume it is differentiable in the open interval a comma b. Then the theorem says that there is some c in the interior, meaning in the open interval a comma b, such that the derivative of f at c is this value. Now what is this value geometrically? So here is a sample graph of the function. So fb minus fa divided by b minus a. What is b minus a? B minus a is that much. Or if I just translate it, it is that much. What is f of b minus f of a? It is that much. So the ratio is the tan of this angle. This is fb minus fa. This is b minus a. So the tan of this angle, or you could say the slope of this line, is same as what is written here. Let me join that line. Right? So this quantity we geometrically understand, it is just the slope of this line. And what is the theorem saying? It is saying that somewhere somewhere in the interior, somewhere here, the slope, or the slope of the tangent to the curve is equal to that. And pictorially, how do we see this? Pictorially, you just take this line and translate above. At some point it will touch the curve, and when it does, the corresponding point that you get is what you seek, is what is guaranteed by the result. So that's roughly the visual motivation for the theorem. Now for the details, one particular way to do it, and that is the way we are going to do it, is to rotate your head. If you rotate your head and make this as the x-axis, then think of this thing as the y-axis, then it becomes Rolle's theorem. You have a function which takes the same value, the value 0 in fact, at the point A and the B and point B. So somewhere its slope must be 0. And now you rotate your head back and you will see that you have a tangent line whose slope is same as the slope of this line. So this rotate your head will be executed analytically. How do we execute it? Define the function h, or the function h, as, so we are proving it. So how do we define h? H of x is equal to f of x minus so we have this function h of x, and if you think about it a little bit, you will see why it is defined this way. So the thing that we observe is that h of a is 0 and h of b is 0. Right? What have we done? Suppose we choose a point x, then what is this? What do we think of this value as? So if you choose a point x, this distance, this much, is what is written here. And if you add f of a to it, it becomes that distance. So once you have an x, let's say this is our x, bad color. If this is x, then this much, this is f of x. This distance is what is written over here. And we have subtracted this out from this much. This is f of x. We have subtracted this out, so all we are recording is these differences, these values. So finally, what is h of x? H of x is nothing but this much. If this is x, h of x is that much, and that is all you're registering. So it is essentially like rotating your head, or that is one way to rotate your head. Okay, all right, and now we have this. Now since f is continuous in a comma b, so is h. F is differentiable in this interval, so is h. And now we can just apply Rolle's theorem to h. Using Rolle's theorem, we have a c in a comma b such that h prime c is 0, which implies f prime c minus because what is the derivative of h? It is the derivative of s minus this ratio. The derivative of this is 1, the derivative of that is 0. So that's it. That proves the existence of that c. Okay, let's move on. So here is a generalization of the previous one. It is not so easy to give a geometric meaning to it, at least for me it's not so easy. So I will just prove it, and this is useful. We will use it at some point, I think. So we have two continuous functions, f and g. Assume that f and g are differentiable on the interior, again, the same kind of hypothesis. Further assume that the derivative of g is never 0. Then there is some c such that this happens. Now, if I really try, I can actually give a geometric motivation for it, but I think it will waste a lot of time. So let me just give a proof. It's a useful result. We will use it later, and let me just write a one-liner for it. So define this function as this minus the same thing for g. And now check that h of a equals h of b. And now apply Rolle's theorem to h. As simple as that. And this is quite a significant statement. Let me just state a few things about its, where is the content. So if we just applied mean value theorem to f, we would obtain a c such that f of b minus f of c is equal to b minus, what am I writing? Such that f of b minus f of a is equal to f prime c times b minus a. We would get that. And if we apply Rolle's theorem, Lagrange's mean value theorem to G, we would get some D such that this happens. And now if we take the ratio, this cancels out, and we get that this ratio that we see over here is equal to f prime c divided by g prime d. So you can always manage with a different c at the top and below. But the theorem says that no, there is one single c which gives this equality. So it's a significant thing. All right. So if you apply Rolle's theorem, you'll immediately get this result. And as a remark, note that if you set g as the identity function, then you recover Lagrange. Then Cauchy's mean value theorem implies Lagrange's mean value theorem. Okay? Now for some consequences of what we just learned. So suppose we have a continuous function and which is differentiable in the interior. So this is the same kind of hypothesis that we have been having. Two things are equivalent. First is that f is increasing. The second is that the derivative of f is always non-negative. So what is an increasing function? Recall, it just means that if x is less than equal to y in the domain of the function, then the values also have the same relationship. So that's just recalling the definition of an increasing function. Okay. So how do we prove this? So first, 1 implies 2. So fix some point in the interior. And we want to show that this is the case. So let me write it. So want to show that this is the case. But now since f is increasing, we have this is the case for all x greater than equal to x naught, and of course in the domain. So this I just simply don't need to write because of context. So this implies this inequality is also there, and now we just take the right limit. This will also be non-negative, but since f is differentiable, the right limit and the limit are the same things. In fact, this right limit is same as the derivative. So this is non-negative. And we are done. Very simple proof. What about the other part? 2 implies 1. So we are assuming 2 and we want to prove 1. So assume on the contrary that 1 is false. So let me draw a picture. If 1 is false, that means f is not increasing. If f is not increasing, then there are 2 points in the domain of the function where the relationship is reversed, meaning it'll look something like that. So maybe there are 2 points x1 and x2 in the domain such that the value at x1 is more than the value at x2. So, but if you apply now the mean value theorem, Lagrange mean value theorem, you'll see that the slope at some point in the middle will agree with this slope, but this slope is negative, and that contradicts 2. So that's essentially the proof, and let me write it. So assume 1 is false, so then there exist distinct points alpha and beta such that f of alpha is greater than f of beta. But now by Lagrange's mean value theorem, there is some c in the interior of alpha and beta, or in strictly between alpha and beta, such that this is the case, but this is negative. Right? Maybe I should have written it the other way. What I wrote was correct, but it's perhaps better to write it this way. So this is negative, and therefore f prime c is negative, but f prime c is negative contradicts the hypothesis. That's it. So that proves that you can, if you knew that your function was nice, you can talk about this sort of a global property in a local way. This is a local property. The derivative is a very, very local object. But if you had some hypothesis on your function, which is this, then you can talk about a global property of the function. That's very nice. So one last thing, a corollary of what we just did. So with the same hypothesis as usual, suppose the derivative was always 0. Then the function is constant. You just apply Lagrange, you'll see it, or you use the previous thing. Because if this is always 0, then this is also true, so the function is increasing. But similarly, this is also true, so the function is also decreasing by the same, the counterpart of the previous theorem. But if the function is both increasing and decreasing, it has to be a constant function. So again, a local property implies a global property, assuming you knew something nice about the function. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.